better. I'm from Intel's Open Source Technology Center, and I'm going to talk a bit about atomic mode setting kind of with driver varieties. Kind of caveat up front, I'm not going to really explain all the kernel mode setting concepts. There's great talks from Maxim Rippert and Laurent Pichard for that. So I'm kind of just going to talk about how do you make updates over various components in your display chain, atomic as in with no tearing, all in the same frame, no kind of ugly effects and unnecessary flickering that people don't appreciate anymore. So it's just going to be about kind of objects, properties, and setting values for them. First a bit of PR, like why should you care? And I'd say Upstream Atomic is pretty awesome because for the first time ever, you can write one display driver and it's going to run on Android. There's a hardware composer that uses Atomic from Google. It works on ChromeOS. It works obviously on X. It supports Western. You get FPDF emulation for free. We have a pretty nice documentation. We're starting to grow a test suite, and I'd say it's a pretty nice community, helpful. With slightly less, a bit more than a year, more than 10 new drivers have been merged, over 10 drivers converted to Atomic. So it really has taken off. We have helpful libraries for everything, so HDMI info frames, display, port handling, tons of different helper libraries to specific for certain hardware. If you have runtime PM, there's something to take care of that. So essentially, finally, after 25 years of trying, Linux has one display API to rule them all, hopefully. So with the PR out of the way, let's dive into what an atomic mode set looks like from a driver point of view. And it's about 3 phases. First, you build up a new state. For backwards compatibility, all these atomic updates are incremental so that all the legacy APIs still work. So you can like move just one plane around and these interfaces still work. Then there's the check phase, where you compute derived state, like how much FIFO space you need, or what kind of clocks you need, or whatever else. And make sure that it actually works. And then the final phase is commit the new state to hardware, possibly asynchronously. So that's already a bit of difference to kind of how, for example, databases do Atomic, where it's a try, commit, rollback approach. Whereas, you kind of can't do that with hardware because try, commit would mean flickering all over the place. So, state building, for every KMS object, the display pipeline, the plain hardware, the outputs and whatever, there's state structures, so like DRM, plain state, and they're all tied together in the atomic, DRM atomic state object. And we do that so that you can do partial updates. So if you have like two users, two compositors, they can both do a partial update on their part of the display pipeline and not interfere with each another. There's hooks to create and destroy these state structures so that you can subclass them and have a place to put your own derived state or whatever you feel like. There's get set property functions, which are for all the driver-specific properties if you have extensions in your driver. What we do in the core, though, is we decode all the properties into kind of the structure and C values in the core for all the standardized stuff. Because otherwise, if the real interface would kind of be the abstract property numbers, writing compatibility code would look really ugly. And if we directly decode the states, the common properties that we also need for legacy support, it looks much nicer. And yeah, if you start to write your own driver, just start with the helpers. There's kind of default functions for all the hooks, and then fill out the details later on, subclass where you need. So now we kind of have this atomic update, bunch of structures. And now we need all assembled together in the DRAM atomic state. Now we need to make sure that it actually is something the hardware supports. And there's just one hook, and that's called atomic check, and that gets the entire state. Plus a really big pile of modular helpers so that you can, one reason is we have like the legacy helper code for the existing drivers, so there's helpers that give you backwards compatibility and just call the old hooks at appropriate places. There's also new atomic jack hooks, which are a per object, where you get the actual state. And you can, for example, if you have interdependencies, I'm going to talk a bit more about that later on, you can first check one set of objects, and then the second, and then the first again, so that you eventually kind of reach the total state of all the dependencies and things. And definitely read the kernel doc for all that stuff, because that explains what kind of helpers to use in which cases. Now, what should you actually do in these atomic jack callbacks? And kind of the recommended way is, very often, your atomic commit needs the same information like the atomic jack. So how many DP lanes you have, what clock you want to run out to, so that you know you have enough clocks, and later on you need to know this to correctly program the clocks. So the recommended way is that you pre-compute that in the check phase and store it in the structures to make sure that there's not a silly little mistake with the values you use in the commit is not actually the values you use in check, and then things mismatch and the atomic commit fails. And yeah, for that, for that, you can subclass the per object state structures. And usually for featureful drivers, you end up with subclassing almost everything. The next one is, of course, there's cross-object dependencies. Like, depending upon how many hardware planes you have, you might run out of FIFO space. So to allocate the FIFO space, you need to check all the planes. And for that, you need to look not just at your own object, but kind of all the others, and maybe even at an object which is not part of your state. And pardon. For that, atomic check hooks can look at any other state. Now, the tricky bit there is you always really need to use the provided functions to look up the state, because to make parallels update possible, we need one lock per object. Now, if you just, in any order, try to acquire these objects and the locks for them, that's obviously going to deadlock. So we resolved that using the wayland mutex magic, which is special mutexes which can detect deadlocks and tell you, sorry, this deadlocked. You need to back off. So the entire atomic update, the check and the commit gets unrolled, and we throw out all the states. We wait for the contending lock, and then we restore the transaction. And since you're probably never going to actually contend for atomic updates, because you just have one or two maybe display, compositors or whatever, there's a wayland mutex slow path debugging support which artificially injects deadlocks to make sure that all that fallback, rollback code in your driver works correctly. And finally, if you, like I said, if you have tricky dependencies where object A depends on B and B depends on A, and you kind of have these loops, you can overwrite the global atomic check and not use the default helper and just call things multiple times. And yeah, since there's 10 plus drivers, there's tons of examples already for figuring out VAR clocks and FIFO space allocation and all these things. Now, with that, you can kind of check cross object states. What about truly global stuff? For example, you have a limited set of display clocks, PLLs, shared across all your display pipelines. And for that, we have a bunch of callbacks to allocate the DRM atomic state, so you can subclass that, add whatever you want there. Pardon. Of course, you again need a lock, so you can either add your own wayland mutex. The deadlock avoidance code works with, it doesn't need to know upfront how many locks are around, so you can just add more. Or in most cases, it's good enough to just use the connection mutex, because if you change the connection routing, generally that's the cases where you need to reassign global state. And so you, in practice, not actually limiting your parallelism. And right now, there's just one driver using that, and that's the I915 driver, which, yeah, uses it for shared display clocks, and also for the core display clock of the display engine that we need to scale according to the maximum pixel throughput. Yeah, whether that changes frequently, you mean the clocks? Well, if you change the output, the resolution. So in that case, you need to shut down the display anyway and then enable it again, so it's going to be slow anyway. The point is, with Atomic, you can tell upfront whether it's going to work or not, or whether user space is asking for a configuration that is not possible. So with that, we looked at state checking at an object level, at the cross-object level, and kind of the global level. So now everything is pre-computed, everything is checked, it's ready to go. We can go ahead and actually commit the atomic update. Again, there's just one global hook. And of course, it's not allowed to fail because of invalid state. It is, though, allowed to kind of fail because you just run out of memory or other things. So it's not perfect atomic. It's really, atomic is meant to kind of tell user space, or give user space information about what's possible from a hardware configuration point of view. And of course, the core guarantees that it always calls atomic check first, but it doesn't guarantee that it calls atomic commit. Because if user space or generic user space wants to figure out what's possible, for example, can I enable this HDMI resolution with the integrated panel, or do I not have enough clocks or whatever, it can do a check only atomic IOCTL call and kind of figure out whether that's possible. Another example is when you have your configuration to composite your desktop, you obviously need to know upfront what's possible so that you know with which surfaces you need to fall back to the GPU. And so there the flow is also you ask the kernel driver first, is this possible? And you can start out with a minimal configuration and kind of extend it until you maximized it. And then once the kernel says, sorry, this is no longer possible, you fall back to the last one that works, render everything with OpenGL into the main buffer, if there's anything left. And then once everything is rendered, you can do the atomic commit, and you know it will still work. And the kernel is not going to tell you, oops, sorry, just Yeah, I was lying. So again, there's lots of helpers that you can just plug in, which will by default use all the old hooks, all per object hooks from the old kernel mode setting helper library, so that you have a smooth transition from old drivers to new drivers. Again, you don't have to use like the default hook. You can take out the individual bits and pieces, and there's kernel doc that tells you which alternate function might be more appropriate. For the actual helper design, the big thing is that plane updates for compositing your desktop and output routing resolution changes, they're completely orthogonal. So, and the atomic jack helpers are all also split up in these two pieces. And the other big thing is the old helpers had this funny idea that partial enabling and disabling was a bright idea. So when you just changed part of your display routing, it disabled that part, left the other stuff intact, and then enabled it new, which meant it was really hard to test all combinations and resulted in tons of bugs. So the new helpers, they get rid of that concept. And if you have any kind of output routing change, resolution change, and you can actually control that. So there's a needs mode set flag that you can set if you need to change something that requires your hardware to be shut down and re-enabled, or you can clear it if you're one of these cases where your hardware is magic and just can do something clever. So you can control that, and it always disables everything first, and then re-enables everything that changed. So the entire pipeline, not just, if just the leaves changed, it doesn't just change, update the leaves. And that means your mode set sequence, and most hardware is really picky about that, is deterministic, and there's not combinatorial testing problem. The other thing that we got rid of is DPMS, which is kind of power saving. It's just that thing died with VGA, although I still have VGA here. Essentially, DPMS had intermediate power saving states between enable, on and off. And that kind of made sense when you had massive big magnets in your CRT screens. But yeah, that modern hardware just doesn't support it anymore. So we re-implemented the DPMS support that KMS, of course, still needs to expose simply by enabling or disabling the entire pipeline and kind of, yeah, removing that complexity because it's pointless. The other bit is also there's lots of old hooks which are deprecated because of these partial updates. There was kind of the special case of, okay, I'm going to shut it down, but I'm going to re-enable it. And the other case was, I'm going to shut it down, but for real, and you need to clean up the resources. So they had all kinds of, there have been all kinds of different hooks with slightly different semantics and confusing. And with atomic, all the resources are tracked in the atomic state. So by simply applying a new atomic state, and then calling atomic state destroy on all the old objects, the helper libraries take, and the core take care of releasing resources at the right time for you. And the last bit is, of course, we had all kinds of state tracking members all over in DRM objects that aren't needed anymore because that state is now tracked in the atomic state structures. But by default, they still get updated so that you can have a smooth transition of your driver. But if you write a new one, just don't call that helper and ignore that and overall, a lot of people who wrote atomic drivers said there's so much less boilerplate required because we removed all these complexities that no one really cares about. So with that kind of out of the way, let's look at what the commit flow actually is. And the first hook that's getting called is prepare FB, prepare frame buffers, and that's simply supposed to make sure the memory is there or any other resources that you need. So set up IOMMU mappings, pin the memory to make sure if you have a driver with dynamic memory management that it doesn't get removed and all that. And the helpers obviously make sure that if any of those fail, it calls the cleanup FB hook in the right order and only for the frame buffers that have been set up already. And then the next step is you swap the new. Before that, the DRAM atomic state was completely freestanding. It was not connected to driver structures at all. And that kind of means in a way, the reason for that is to make sure that you don't accidentally touch driver state in your atomic check, because that would mean the check-only functionality would change your driver state, and that's a no-go. So by making the thing entirely freestanding, it's very easy to review drivers and make sure they don't touch something they shouldn't. But obviously, we need to take all these state structures and store them in per object pointers. And that's kind of the first step in the commit. And that's the last step that needs to be done synchronously, because if you do the entire commit asynchronously, obviously the next atomic commit needs to be able to see the new state already. Otherwise, you get chaos and things get out of sync. And everything after that is asynchronously. So the next step is wait for fences and for buffers to be ready, so any rendering to complete and all that. Then it comes to actual hardware commit. I'm going to go into more detail with that one later on. And then you need to wait for 1B blank to make sure that the old buffers are no longer in use. And then you can call cleanup FB on all the old buffers to release the memory and unpin them and destroy IOMMU mappings or whatever, although generally you want to cache those. So let's look at the actual hardware commit step. So yeah, like I said, for the actual mode set that changes the routing and the mode, we have a bunch of objects there in KMS speak, CRTCs, encoders, bridges, it's just names. So that's first done with enable and disable hooks. So to make sure the new routing is there and the new resolution. And then the next step is updating the planes for your desktop compositing. And that's a three-phase thing. First, there's an atomic begin hook on the display pipeline object. And depending upon your hardware, you can use that to make sure you're not in the critical B blank section where things get committed in the hardware, or you can clear like go bits to make sure updates get stalled, or whatever kind of support your hardware has to make sure that all the register bytes go in one step. And then there's a loop of per plane atomic update or disable hooks. And then at the end, an atomic flush where you can clear the go bit, flush out the register bytes to the hardware, or yeah, whatever you need to do to actually commit things to the display engine. So that's essentially how to commit an atomic state. Like I said, all the atomic states are incremental updates. So you have a bootstrapping problem because somewhere you need to start at driver load. And at driver load, the atomic state structures need to match the hardware state because the new helpers assume they always perfectly reflect the hardware state so that they only do the minimal thing. Whereas the old helpers sometimes just disable things harder because state tracking there is not as accurate. But that had the problem that some DisplayPort controllers, for example, really don't like it when you disable them twice. So tons of code. Now, there's kind of two ways to bootstrap your atomic state. One is what pretty much all the drivers do right now, and there's a bunch of reset hooks per object where you just reset the state and assume that everything is off or shut it all down. And in that fashion, kind of make sure that hardware state matches your software tracking. The other option, instead of resetting everything to off, is that you actually read out the hardware state, and then you can do fancy stuff like fast boot, U-boot, or your firmware sets a mode, and your driver just takes over that state and keeps on booting without doing anything. And that's currently implemented by the Intel driver, but since it's just one driver, there's no helper support for hardware state readout. There's a few good tricks in the Intel driver that might be worth extracting. So yeah, that's how you bootstrap your state to make sure you have the incremental updates all actually work out. Then there's lots of legacy entry points, of course. And there's helper implementations for all of them. And they're not used by default, so that if you have an existing driver that has a very specific feature that kind of doesn't make sense to port over to Atomic, you can have your own legacy entry point still, and then do if special case, do the old magic, else use the Atomic helper. So that's why you need to set them explicitly. And of course, like I said, KMS has full FBDEF support. You get that for free. If you don't want it, there's a config option. You can kill it. Then other nice stuff that was fairly recently added over the last 2-3 kernel releases is suspend resume helpers. Since you have all that accurate state tracking, you can capture the software state, then shut everything down, and on resume, first reset everything so it matches again, and then restore the old captured state. And we have a few helpers so that you can, well, 2 suspend resume default helpers, but they are, of course, again, exposed the components so that instead of resetting, you can do harvest, readout, or whatever. Sure. So the question was why I need to capture the state, because it's already there. I need to make a copy, because when you do the commit to shut down everything, the committed state now has everything to off, so yeah, you don't want to save the shutdown state, but when everything was still on, and yeah. And I mean, the only really tricky bit there is because these helpers drop the locks, of course, so if your driver does something silly and changes state between suspend resume, it's going to fall apart, of course. So that's the caveat, which, again, is documented. We also changed the helpers a bit to make them much more useful for runtime PM. That the reason for why they've been really useful for runtime PM is because the old helpers worked a certain way, and I wanted to have as close as possible backwards compatibility for the existing hooks. so that converting drivers to atomic is as easy as possible. But the old hooks kind of changed the planes when everything was shut down, so in between, after you disabled everything and then enabled everything for display routing changes. And of course, when everything is shut down, then your register writes are going to go nowhere. So that's why we added a few more hooks, functions and implementations that do this the other way around, so that you update the planes when the hardware is actually running and your register writes go somewhere. And the other thing is that's now happening and already started somewhat is Intel has since a few years, 4 years now, a test suite for KMS and the GPU rendering side. But it is Intel specific. And a few people are now working to make that generic using the dumb untiled buffer support that KMS exposes for boot splash screens and stuff like that. So that all the regression tests in the IGT test suite can be used on any driver. And initial support is there already. There's a big patch series to convert over the first KMS test cases. So that's ongoing. And of course, regression tests are awesome. There's still a few gaps. One is async commit is kind of not supported by the helpers because for a simple case, you just do scheduled work and it's done. But if you have tricky dependencies between different updates, then it's really hard to create something that is generic and useful and not horrible. So yeah, essentially we don't have it because for simple hardware, it's easy to type yourself with scheduled work, and for complex hardware, you probably don't want to have helpers because they just get in the way. Like I said, state readout for fast boot is not there yet. But I've seen people work on kind of state readout fast boot support with some atomic drivers now, so maybe it happens. Another bit, the DRM KMS has been behind FBDEF for forever is simple drivers. Essentially, you have just a dumb panel. And all these different stages in the KMS pipeline are overkill. And I've tried to sign up someone to kind of do a DRM simple pipeline object thing that collapses everything down to one thing since forever. And it finally happens. There's an RFC. So that's great. And the other bit is if you really care about FBDEF and have one of these manual upload displays or whatever, we don't yet have deferred I/O support in the FBDEF emulation. But there's already like 3 copies and drivers of that code. And someone submitted a new copy. So I asked them to please extract those and put them into the helper. And so that's kind of happening hopefully real soon too. The other thing is kind of extensions for beyond the default legacy kernel mode setting properties. And that's really easy to do with properties. You just add more. And there's 4.7, I think, we just merged support for color management. So a D-gamma color conversion matrix and gamma table, or the other way around. I'm not an expert in that. There's patches floating around for plane blending. So if you have alpha channels, that you can not just composite, can composite with alpha channel. There's been patches floating around for background color. It's really nice if you have like a video and don't want to waste energy scanning out black for the borders. And the approach we've done thus far is that all the standardized extensions, we put them into the core state structures so that drivers don't have to deal with decoding them to kind of reduce duplicated kill. And the thing is, it's One problem a bit is same rules apply like any other kernel API in DRM, which means we need open source user space. And people using that for Android sometimes have a bit of a problem with that. On the topic of Android, it's finally happening. The big thing missing for Android is the fence support. So for context, there's kind of two ways. If you have multiple hardware blocks, like a display engine and a GPU and maybe a video ISP thing or whatever, there's two approaches how you make sure that the next piece of hardware in your pipeline doesn't start processing before the old one is done. And one is implicit fencing, where you just pass around buffers. And the kernel internally, without showing anything to user space, adds synchronization fences to these buffers. So when the next consumer takes the DMA buff and schedules the next step in the rendering pipeline or display, it also takes out the synchronization fences that are implicitly attached. But Android works different. With Android, you pass around the buffer object and the fence explicitly as separate file descriptors. And that code has been in driver staging since forever. So Gustavo here is now destaging that. And we are adding for the atomic side in and out fences. So for synchronization, before you scan it out and when you're done with it, for the hardware composer. There's also people working on adding fence support to Mesa's GL stack. Maybe you've heard, I think the Nexus 5 is booting on Upstream with the open source MSM GL driver. Android is booting Android on Upstream. And of course, right now, it's kind of not doing a whole lot. But people are working on that, and that's pretty much, as far as I know, the last bit for proper Android support. The DRM hardware composer that Google has right now just kind of fakes the fences in user space. And of course, the point is that you do them in kernel so that you have lower latency. Documentation, because, yeah, a pile of links. I mean, the slides are online. There's a conversion how-to if you have a legacy driver, but those are kind of running out. There's a two-part LWN series that explains atomic in depth and goes a bit more into details than what I explained here. The DRM developers manual, which I think for 4.5 we updated all the vtables documentation, so it doesn't look all that pretty because the DRM, the kernel docbook toolchain is a bit awful, but it's all there. And the IGT test case suite also has docs for all the core functions that you need to run test cases. So with that, short summary of Upstream Atomic. There's three phases of an atomic IOCTL. First state building, then checking, and then optionally commit if you don't do a check only. We have modular helpers for almost everything, and you can mix and match them. And there's docs that explain how to do this. There's test cases, or real soon there's generic test cases. And I guess the really nice thing is also is an active cross-vendor community. If you look at the initial atomic support that was developed in 2014, in fall 2014, I think it's like 5 or 6 different companies that worked on that. So it's not just like Intel and Red Hat like before. And it supports everything from FPDEV to Android. So thanks a lot for listening, and any questions? Yeah, I'll repeat them.
How efficient regarding the
So the question is for fast boot, or if you recover all the state, what about the frame buffer and the memory allocation of the frame buffer? And I can't tell how we did this in general, but I can tell you how we do it in the Intel driver. There's a carved-out region that is only used by graphics that the BIOS firmware reserves. And the initial frame buffer is in there. So when we boot up, we look at the hardware registers and look at the offset, and then blindly assume that the BIOS firmware has done the default mapping between the graphics IOMMU and that carve-out region, just one-on-one map them. And then we reserve that memory and wrap it into a proper DRAM frame buffer object and attach it to the state object. So when you do the next mode set, it's going to call cleanup for FB on the old frame buffer and release that memory. But yeah, you need to wrap it. I guess the other thing you could do is just not enable the plane, just shut it down. Because usually what takes time is changing the output routing and the mode and not changing the planes. So if for some reason you can't reserve that frame buffer memory because the kernel is there or whatever, you can just disable the plane hardware when you take over and you still have fast boot. It's just black. Other questions? I guess otherwise, that's it. Thanks a lot for listening.